I want to motivate this course on total non-negativity and the Hickey algebra by starting with another algebra called the Tmperley-Lieb algebra. So I'll write it Tn of delta. Delta is a complex number. This is generated by elements little t1 through little tn minus 1, subject to the relations any generator squared is delta times that generator. A product of three generators of the form ti, tj, ti is just ti if I and j differ by 1. And generators ti and tj commute if I and j differ by at least 2. So for example, if we want to compute ti t1 plus t1 t2 times t2 plus t2 t1, that equals t1 t2 plus t1 t2 t1 plus t1 t2 t2 plus t1 t2 t2 t1. And then we can simplify that using the relations. Well, t1 t2 doesn't simplify. t1 t2 t1 is just t1. t1 t2 t2, we don't need two t2s in a row because of that first relation. This is going to be delta t1 t2, and then here again we don't need two t2s in a row. That's delta t1 t2 t1, and then t1 t2 t1 is just t1. And we can group together, I guess, just these two terms and write it as t1 t2 plus 1 plus delta t1 plus delta t1 t2. Now let's do another example. I'll keep the presentation here so that we can look at it. And let's just simplify a big old monomial. Let's look at t1, t2, t3, t1, t2, t3, t1, t3. How does that simplify, if at all? Well, it does. We see we can almost have a t1, t2, t1 here. The 3 is in the way, but t3 and t1 commute because their difference between 3 and 1 is at least 2. So I can swap these, and then I'll get a t1, t2, t1, and a t3, t2, t3. And then t1 and t3 commute. I might as well put the 3 first because it's going to cancel a t3 there. Okay, now this becomes just t1, and this becomes just t3, and then this t3 next to that t3 just creates a delta, so I'll write this, and then t1. But t1 and t3 commute, so we can put the two t1s next to each other and get a delta squared t1 t3. So this whole big monomial simplified down to delta squared t1, t3. All right, now I want to do this example over again from the point of view of Kaufman, who was a knot theorist that thought of a different way to look at the Tmperley-Lieb algebra. I'm going to put the generators and relations up here so we can still refer to them and compare Kaufman's version to the version we just did. All right, his version says that our generators are pictures that consist of horizontal lines and a C and a backwards C. And that C and backwards C appear in all possible positions from top to bottom. And we have n endpoints of arcs here. So we have the C in the top two positions, or the next two positions, the next two positions. So there's n minus 1 different possibilities for where the C and the backward C goes. Now we multiply by concatenation. That means gluing together. And then we don't have to really worry about the relations because these pictures do that for us. So in addition to concatenating, sometimes we're going to get bubbles. We're going to pull out a bubble and make it a delta. So for instance, let's say n is 4. So if we multiply these two generators together, we glue them by connecting the corresponding dots. And then we sort of mark every bubble, and then that bubble comes out and becomes a delta. And then we pull all the strings kind of tight to make it into one of these pictures, or a concatenation of several of these pictures. So this generator that said that this relation that said any generator squared is delta times the generator comes just by gluing the picture together, taking out a bubble, making it into a delta, and putting it in front. So that relation is already taken care of. Now let's see that the second relation is already taken care of too. These indices differ by exactly 1. That means that we're doing multiplication something like this. So the C's are just one level apart. And then if we pull all the strings tight here, we find that we get this picture, because that bottom string just gets pulled tight to be a straight line. So if we chop this up, this is ti, ti minus 1, ti, that are just getting glued together and stretched a little bit to make another ti. Okay, so that relationship is taken care of. And obviously if this were ti plus 1 instead of ti, then this picture would just be flipped upside down and the same thing would happen. Now if I and j differ by at least 2, that means that we have pictures that look like this. And when we glue that together, we get this picture, which is the same thing we would get if we glued in the opposite order. So indeed, this third relation is taken care of also. All we have to do is remember the pictures. So now let's do the same two examples that we did before. Let's let n be equal to 4. And then we have, let's see, T1. Actually, I could even let n be equal to 3 for this. T1 plus T1, T2 times T2 plus T2, T1. So glue these together and we get this. Glue these together and we get this. Then glue these together and we get this, and then finally glue those two together and we get this, and then pull all the ropes tight. This picture looks like that. This picture looks like that. This picture, let's see, make that a delta, make that a delta. Delta times this thing, and then delta times that thing. So we just did this computation over again without even really thinking about what the relations are. All we had to do was look at the pictures and pull some strings tight, take the bubbles out and make them deltas. Now let's do the other example. Now I'm going to let n equal 4. The other example was 1, 2, 3, 1, 2, 3, 1, 3. So 1, 2, 3, 1, 2, 3, T1, T3. Okay, we've got two bubbles in here, so let me put marks on them so they can come out and become deltas. And then this rope pulls tight to make that shape, and then these two ropes are like that. So there we go. So we simplified this whole big long binomial just by pulling strings tight. So obviously we don't need every possible monomial in the t's. This is not an infinite dimensional algebra. Or maybe we can't see that right now. But we know we don't need every possible combination. Turns out that the dimension as a complex vector space of the Tmperley-Lieb algebra is 1 over n plus 1, 2n choose n. Now that's not too easy to see from this set of generators and relations. Using the pictures, it's a little bit easier to see. So if we glue together the Kaufman generators in all possible ways, we get non-crossing perfect matchings of 2n vertices Oh, I'm going off the picture a little bit. Where all of the edges connecting these stay in the box. So we can have things like this and that, etc. But the edges connecting these vertices can't go outside of that rectangle. So let's do all of these for n equals 4. So 1 over 4 plus 1, 2 times 4, choose 4, is 1 over 5 times 8 factorial over 4 factorial, 4 factorial, which is 8 times 7 times 6. Don't need the 5 because it cancels this 5. Don't need 4 factorial because it'll cancel one of these over 4 factorial. 3 factorial is 6, and 4 under 8 makes 2 times 7, so there should be 14 Kaufman diagrams of size 4. Well, this is the most obvious one where the edges all go straight across, and then we've got 3 generators. Ten more to go. We've got first generator times third generator, and then first times second, second times first, which are different. And then that thing backwards. Oops, that's only 3. There we go, 4. And then these things can happen between the last 3 levels. So here we go. So now we have 9. So I guess there's 5 more. Here's another matching where the edges all stay in the box, and then its mirror image. And then we have a generator like, a basis element like that, and its mirror image. And then finally, this last matching. So hopefully that's 14. 5 and 5 and 4 is 14. Now still, I think we can't really eyeball it and say that 1 over n plus 1, 2n, choose n, is the number of diagrams. I'm sorry, this went off the bottom. There they are. But pretty soon we'll look at a counting argument that helps us decide that yes, that is actually the formula. And that is the end of this lesson.